morning, everybody. I am R Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering. Today, I am going to discuss about the Mosfet scaling in VLSI design subject. VLSI fabrication technology, it is still in the process of evolution, and this is leading to smaller line widths and feature sizes. Thereby, it is causing higher package densities in the chip. The scaling down of the feature size generally leads to enhanced performance, so it is necessary to understand the effects of scaling. Of course, there are future limits to scaling which may well be reached soon. The microelectronic technology, it is characterized by several indicators such as minimum feature size, number of gates on the chip, the power dissipation, and the maximum operating frequency, the die size, and the production cost. So the microelectronic technology is characterized by all these metrics. To study the effects of scaling, so the phenomena of scaling can be best described by three models. The three models are constant electric field model, constant voltage model, and the combined model. So these models, they present a simplified view taking only the first degree effects into the consideration. And they are easily understood and they are well suited to all educational needs. So in order to accommodate all these three models, that is the constant electric field model, the constant voltage model, and the combined model, there are two parameters which we are going to use. They are alpha and beta. And alpha is used for the linear dimensions and beta is used for the supply voltage and the gate oxide thickness. So for combined model, we are going to use both alpha and beta, where alpha and beta are greater than 1 and typically they assume a value of 1.4. For constant field model, alpha is equal to beta, and for constant voltage model, beta is equal to 1. Now I will give you a pictorial view of N Mosfet showing the linear dimensions. So this is the substrate, and for N Mosfet we use a P substrate. And this is a gate which is made of the polysilicon. So polysilicon exhibits the metallic properties. So this is a polysilicon gate, and polysilicon gate is represented by the orientation of lines in this direction. And you know the polysilicon is separated from the substrate by thin oxide. So this is the thin oxide layer which acts like a dielectric. So I am putting dots here which represents the thin oxide. Okay. We have the source and the gate regions. Source is N plus and drain also is N plus. And N plus diffusion is represented by arrows inclined in this direction. So this is a P-type substrate. P-type substrate is represented by inverted V in this way. You know that the N MOSFET is formed on the P substrate, and if you take P MOSFET, it is formed on N substrate. And P substrate is formed by passing boron gas into the wafer, and N substrate is formed by passing phosphorus gas. So this is N plus source and this is N plus drain, and this is a polysilicon gate. Source, this is drain, and this is gate. The dimensions are like this. This is the length of the channel L, which is scaled by alpha, and the width of the gate is W. So this is the width of the gate W, and this is also scaled by alpha. Okay, and the oxide thickness D, that is scaled by beta. So we are using the parameters alpha and beta. Alpha is for all linear dimensions, and beta is a factor which is used for scaling down the supply voltages and the thin oxide thickness. Now, one by one, let us see the effects of scaling on the MOSFET parameters. First is the gate area. What is gate area? This is length L and this is the width W, right? So, what is the original gate area? AG is equal to WL. So, when you do the scaling, the area is going to change. The area is going to reduce. So, it becomes AG dash. And W is going to become W dash and L is becoming L dash. What is W dash? Just now we have told you that the width is going to be scaled by alpha. So W dash becomes W by alpha. And L dash is nothing but L by alpha. So this is equal to 1 by alpha square WL. It means to say that AG dash is equal to 1 by alpha square AG. So we can clearly say that the gate area is scaled by the factor 1 by alpha square. So the gate area is scaled by 1 by alpha square. Now, similarly, let us see the effect of scaling on the gate capacitance per unit area. In N MOSFET, the polysilicon is separated, polysilicon and the channel, they are separated by thin oxide. You know, whenever any two metal plates are separated by a dielectric, you are going to have a capacitive effect. So that capacitance is called as the gate capacitance. And what is the standard formula for capacitance? The standard formula for capacitance is epsilon A by D. And So let me write, the standard formula is C is equal to epsilon A by D. And what is the unit area gate capacitance? Capacitance per unit area. So I am going to call it as C naught. So that is going to become epsilon by D. What is epsilon? Epsilon is equal to epsilon Vx and epsilon naught divided by D. Okay. So epsilon Vx is the permittivity of the gate oxide, which is nothing but epsilon ins into epsilon naught. Okay. So epsilon Vx is equal to epsilon ins into epsilon naught. So epsilon ins, it is a permittivity of the thin oxide, and epsilon naught is a permittivity of the free space. Okay. Now when you do the scaling, CO becomes CO dash. So what is CO dash? CO dash is equal to, okay, epsilon Vx dash by D dash. And scaling is not going to change the fundamental properties of the material. So epsilon Vx is not going to change. So CO dash is equal to epsilon Vx is not going to change, but D dash, that is the thin oxide thickness, I told you that it is going to be scaled by the factor beta. It is going to reduce by the factor beta. So D becomes D by, D dash is nothing but D by beta. So I can write this is equal to 1 by beta into epsilon Vx by D. So it means that CO dash is equal to 1 by beta CO. So the gate capacitance per unit area is scaled with a factor. See, D becomes D by beta. So here you get beta. So CO dash is equal to beta CO. So to summarize, the scaling increases the unit area per gate capacitance, because CO dash is equal to beta CO. Now let us see the effect of scaling on the other parameter, the gate capacitance. What is gate capacitance? So gate capacitance is Cg. So that is equal to, you have to take the unit area gate capacitance CO and you have to multiply it by A. What is A? A is width multiplied by the length. So Cg dash is equal to CO dash into A dash. So what is CO dash? Just now we discussed that the unit area gate capacitance increases by a factor beta. So CO dash is equal to beta CO, and the area reduces by a factor 1 by alpha square A. So this is equal to beta by alpha square into C naught A. What is C naught A? Which is nothing but Cg. So Cg dash is equal to beta by alpha square into Cg. So you can very clearly understand that the gate capacitance is scaled by beta by alpha square. See, alpha and beta both are greater than 1. Typically they have a value of 1.4. So beta by alpha square is less than unity. So scaling effectively reduces the gate capacitance, which is good. Now let us go to the next parameter, that is the parasitic capacitance Cx. There are drain, source and gate terminals and depletion layer in the Mosfet. So all these things they cause parasitic capacitances, and this parasitic capacitance Cx is proportional to Ax by D, where D is the depletion width around the source or drain, and this is scaled by 1 by alpha, and Ax is the area of the depletion region around source or drain, and this is scaled by the factor 1 by alpha square. So the Cx is scaled by 1 by alpha square into 1 by 1 over alpha. So you can say that the Cx is scaled with a factor 1 by alpha. So the parasitic capacitances are scaled with a factor 1 by alpha. That means the parasitic capacitances are reduced due to scaling. Now let us see the effect of scaling on the carrier density in the channel. See, whenever you apply a positive voltage to the enhancement Mosfet, it attracts the minority charge carriers from the P substrate and a channel is formed between the source and drain. This channel contains the carriers, the induced carriers. So what is the effect of scaling on these induced carriers in the channel? That is the thing what we have to study. And what is the standard formula for capacitance? You know, standard formula is C is equal to Q by V. So you can say that Q is equal to CV. So Q on is equal to C naught VGS. You are applying a voltage between gate and source. So due to that, charge carriers are developed. So Q on is equal to C naught into VGS. So because of scaling, Q on becomes Q on dash and C naught becomes CO dash and VGS becomes VGS dash. What is CO dash? You know, it is a unit area gate capacitance and that is increased by a factor beta. And VGS dash is a new gate to source voltage, and I told you that all the gate to source voltages and drain to source voltage, they are scaled with a factor 1 by beta. So VGS dash is equal to VGS by beta. So this they get cancelled. So you get same C naught VGS. So that means to say that Q on dash is equal to Q on. So the scaling does not change the carrier density in the channel. It remains unaltered. Now let us see the effect of scaling on the channel resistance. The channel resistance, it is given by this formula RO on is equal to L by W by 1 by Q on mu. Mu is the mobility of the charge carriers. If it is N MOSFET, you have to take the mobility of electrons. If it is P MOSFET, you have to take the mobility of the holes. And L is the length of the channel, W is the width of the gate, and Q on is the carrier density in the channel. So when you do the scaling, RO on becomes RO on dash, L becomes L by alpha, W becomes W by alpha, and Q on becomes Q on dash, and mu is this. Okay. So what happens? You have alpha here and alpha here. So you get here L by W and Q on. Just now we discussed that there is no effect of scaling on the carrier density. So this remains same Q on and mu. So we can say that RO on dash is equal to RO on. So scaling does not change the channel resistance. Okay. Let me explain it more logically. If this is the channel, okay. So you from here to what is the property of the physical material? When you reduce the length, naturally the resistance reduces. But when you reduce the thickness, the resistance increases. So if you think that this is the channel, the channel L is getting reduced because of scaling. L becomes L by alpha. At the same time, the thickness also reduces. So though the resistance gets decreased by the decrease in the channel length, it is nullified. The effect is nullified because the thickness is getting reduced, which increases the resistance. So the increase in resistance is nullified by the decrease in resistance because of the decrease in the channel length. So, to summarize, there is no effect of scaling on the channel resistance. Now, let us see the effect of scaling on the gate delay. In Vlsi circuits, the desirable factor is you should have less delays so that the signals travel from one point to another point with good speed. So, what is desirable is gate delay, minimum gate delay. And gate delay is given by the RC time constant. TD is equal to RC time constant, and R you have to take the channel resistance RO on, and capacitance you have to take CG, because gate capacitance is more predominant in the Mosfets. So, what is TD dash? It is the new value of gate delay because of scaling, that is equal to RO on dash multiplied by CG dash. And just now we discussed that there is no effect of scaling on the channel resistance. So RO on dash is equal to RO on. And what is the effect of scaling on the gate capacitance? We told you that the gate capacitance is scaled by the factor beta by alpha square. So you put the same value, beta by alpha square CG. So this is equal to beta by alpha square RO on CG. So TD dash is equal to beta by alpha square TD. So we can say that the gate delay is scaled by the factor beta by alpha square. And alpha and beta typically they have a value of 1.4. So beta by alpha square is less than unity. So you can very easily conclude that the scaling reduces the gate delay, which is good. Next is the maximum operating frequency. The maximum operating frequency is given by this formula. F0 is equal to W by L mu C0 VDD by CG, where W is the width of the gate and L is the length of the channel, mu is the mobility of the charge carrier, and C0 is the unit area gate capacitance, VDD is the supply voltage, and CG is the gate capacitance. So when you do the scaling, F0 becomes F0 dash, and W becomes W dash, L becomes L dash, mu. Mu, the mobility of the charge carrier, it does not change with respect to scaling. But C0, the unit area gate capacitance, it increases by a factor beta. Okay. So let me write CO dash VDD dash by CG dash. So W becomes W by alpha, L becomes L by alpha mu, CO is beta C0, and VDD dash is VDD by beta, and CG dash is beta by alpha square CG. So this is equal to W by L mu C0 VDD divided by CG and alpha square by beta. So F0 dash is equal to alpha square by beta into F0. So the maximum operating frequency is scaled with the factor alpha square by beta. Alpha and beta both are greater than 1. So the maximum operating frequency increases due to scaling. So this is desirable. Next, let us see the effect of scaling on the saturation current, IDSS. So IDSS is given by this formula C0 mu by 2 into W by L into VGS minus VT whole square. So what happens to the saturation current? because of scaling. Okay. So what is the formula for the saturation current? IDSS is equal to C naught mu by 2 into W by L into VGS minus VT whole square. Okay. So IDSS dash is a new value of the saturation current because of scaling, and CO, CO becomes, this is CO dash, mu is same, it does not change, and W dash L dash VGS minus VT, VGS dash VT dash whole square. So CO becomes beta CO mu by 2, and W and L, they are scaled with the factor alpha, so you get the same value, W by L. The voltages are scaled with the factor beta, so you take beta outside, so you get 1 by beta square into VGS minus VT whole square. So here you get 1 by beta C naught mu by 2 W by L into VGS minus VT whole square. So IDSS dash is equal to 1 by beta IDSS. So the saturation current is scaled by the factor 1 by beta. So that means the saturation current decreases due to scaling. Now let us see the effect of scaling on the current density. What is the current density? J is equal to I by A. Okay. So J is equal to IDSS by A you take, and A is the cross sectional area, which is nothing but W by L. So J dash is equal to IDSS dash divided by A dash. So this is the, just now we discussed that IDSS is scaled by the factor 1 by beta. So that is equal to IDSS, and the area is reduced by the factor alpha square A by alpha square. So J dash is equal to alpha square by beta J. So we can say that the current density is scaled by the factor alpha square by beta. Next is the switching. In the same way, you can analyze the other parameters. There is a switching energy per gate. What is the energy formula? E is equal to half CV square. So EG is equal to half CG into VDD square. EG is scaled, CG is scaled by the factor beta by alpha square. So we have written this beta by alpha square. And VDD, voltages are scaled by the factor 1 by beta. So we write here 1 by beta square. So we can say that the EG is scaled by the factor 1 by alpha square beta. Next, let us discuss about the power dissipation per gate. The power dissipation, it contains two components. The two components are PGS and PGD. And PGS is given by VDD square by R on, and PGD is given by EG F naught. So you can very clearly see that PGS and PGD both are scaled by the factor 1 by beta square. So we can say that the power dissipation is scaled by the factor 1 by beta square. Next is the power dissipation per unit area. PA is equal to PG by AG. And what is AG? AG is the gate area. So we can say that the power dissipation per unit area is scaled by the factor 1 by beta square by 1 by alpha square. So it is scaled by the factor alpha square by beta square. The final parameter is power speed product PT, which is given by PG dot TD. The PG just now we discussed that it is scaled with a factor 1 by beta square, and delay is scaled by the factor beta by alpha square. So we can say that the power speed product is scaled with factor 1 by alpha square by beta. So we discussed about the scaling effects on various parameters using a combined model. So in combined model, we have considered both alpha and beta. And alpha and beta both are greater than 1. Typically, they have a value of 1.4. Okay. So here you see, these are the various parameters, and this is the formula. Formula is what we have derived just now using a combined model. Supply voltage is scaled by the factor 1 by beta, and gate area is the first parameter what we have discussed, and we told you that it is scaled by the factor 1 by alpha square. Then C naught beta, gate capacitance is scaled by the factor beta by alpha square. Parasitic capacitance is scaled by 1 by alpha. Carrier density, there is no effect of scaling on that, so it remains as 1. Channel resistance, it remains as 1. Saturation current 1 by beta, and current density alpha square by beta, and switching energy 1 by alpha square beta, and gate per unit area alpha square, and gate delay beta by alpha square, and power speed product 1 by alpha square beta. See, for a constant electric field model, the formulas are obtained by substituting alpha wherever beta is there. So you have to assume that alpha is equal to beta for constant electric field model. For example, if you take the power speed product is 1 by alpha square beta. So you put beta equal to alpha here, you get 1 by alpha cube. Similarly, the maximum operating frequency alpha square by beta. So you substitute alpha for beta. So alpha square by alpha, you get alpha. So like that, you get the formulas for constant electric field model. And to get the equations for the constant voltage model, you assume that beta is equal to 1. So wherever beta is there, you assume that it is 1. For example, you take this parameter, power dissipation per gate is 1 by beta square. And beta is equal to 1 for constant voltage model, so it becomes 1. Okay. Similarly, switching energy, it is 1 by alpha square beta for a combined model, and for constant voltage model, it becomes 1 by alpha square because beta is equal to 1 for constant voltage model. So, we have studied the effects of scaling on the different Mosfet parameters, and we have seen that it improves almost all the parameters. It improves the maximum operating frequency, and also it improves the time delay, and it improves the gate capacitance, and so on. With this, I conclude today's topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.